Alright, so the last thing we're going to take a look at in section 11.2, the first part, is how could we add up numbers like this? We can probably see what the pattern is. Looks like there's always a 2 in the top. But what's happening to the number in the bottom each time?
Multiplying by 3.
Yeah, it's multiplying by 3. So if I wanted the next number after 2/9, what do you think it would be?
2/27.
Right, 2/27. So the question is, if you did that 12 more times and then wanted to add all of them up, 2 plus 2/3 plus 2/9 plus 2/27, all the way to the 12th one, what would they all add up to? Well, we could figure them out. Right? We could find all 12, add them up. That's not that bad. But if it said, to do the 120th partial sum, do we want to find all 120 terms and then add them all up? No, that's going to take a while to figure out. So there's a formula for figuring out the sum of adding up all those numbers as long as the pattern is geometric. So remember what geometric means. Geometric means to get from one term to the next, you multiply, yes. As long as the pattern is multiplying, this formula will help us to add everything up. Hey, let's label it and see if we remember what's what. What do you think A1 is?
The first in the sequence.
Yeah, it's the first term. So it's your first term. And then R, same in the top and the bottom. R is, we called it the common ratio, but it's really just the number that you're what?
Multiply.
Yep. So that's the number you multiply by. And that's how many terms you want to add up. So if you want to add up, go back to it for a second. If you want to add up 12 terms, n would be 12. If you want to do 120, it would be 120. So now it doesn't really matter how many terms you want to add up. It just changes the number you plug in for n. It doesn't really make it any more or less work because we're just going to use a calculator. Number of terms to add. Okay, and not a formula that you need to memorize. You can put that on your reference sheet. You can use that on the test. So that's one I would put down. Okay, so that's the sum of a finite geometric sequence. Does everyone have the formula? All right. Now let's, instead of doing it for the 12th partial sum, let's do it for the 4th, because 4 is small enough that we can quickly check it by hand and make sure that all 4 of those add up to what the formula says. Okay, so let's find the 4th partial sum. All right. So can someone remind me what is the formula that I just gave you for adding up all those numbers? Yeah.
1 minus r to the n. Oh, yeah.
Like that? Yep.
Over 1 minus r.
Okay. Anything else?
Yeah.
And then a sub 1 is in front.
Yeah.
All right. So let's try it for adding up the first 4 terms in that sequence of numbers. Okay, you know what? I'm going to add the 4th one up here. 2/27. Okay, what's the first term in that sequence? 2. Yep, we get a 2. Times 1 minus, and now we got to figure out what we're multiplying by each time. So Alex, let's just look at this one. To get from 2/3 to 2/9, what did you multiply the top by?
1.
1. And what did you multiply the bottom by?
3.
3. So overall, what are you multiplying by?
1/3.
Exactly. Yep. So R in this case is going to be 1/3. And N is how many terms we're going to add up. 4. Yep. We're going to add up 4 terms. So now we're going to type that in and see what we get. Okay, what we might want to do is just simplify the bottom. If you have 1 minus 1/3, what's that going to be? Well, Lance, what's 1 minus 1/3?
2/3.
Yeah, 2/3. The only reason I would do that first is because it's going to be a little easier to type that in on the calculator. All right, so when I type that in, because there are a lot of parentheses and exponents there, I want to do it in several steps. Okay, so first thing I'm going to do is 1 minus, open a parenthesis, just like we have written down. Put in 1/3, and I'm going to raise that to the 4th power. Okay, so that's the numerator. And then we want to divide that by what? 2/3, yep. So we're going to hit divided by, and again, put it in parentheses. 2/3. And then the last thing I have to do is multiply by what's in front. Sean, what's in front? 2. Yep, times 2. Okay, so we get about 2.96. Now I'm going to check that by taking the terms that we had and adding them up by hand and see if I get the same thing. Okay, what was the first term that I had in my sequence? 2. All right, so let's take that. Let's take 2. Plus, and the next one? 2/3. 2/3. The next one? 2 ninths. And the last one? 2/27. So if we did everything right, we should get 2.96. We get exactly the same thing. So that formula gave us a quick way. Now, did it save us a ton of time with 4 terms? Not really. I could have just added these up pretty quick. But where it would save me time is if it said add up the first 500 terms. It's going to take a long time to type in 500 numbers and then add them up. Okay. Versus just putting the number 500 in and using your calculator. Yeah.
I just have a question. To get the 1/3, I know you got the 3 because you multiply it by 3. Did you change it to 1/3 or?
For R?
Yeah.
So R is what you multiply by to change this into that.
Oh, okay.
Yeah. Or you can look at what you multiply by to change this into that.
Yeah, yeah. Now I see it. You just multiply the numerator by 1.
Yeah, the numerator gets multiplied by 1 because it stays the same.
Now, would you have problems that you multiplying both the numerator and the denominator? Or?
Generally, no. It's usually just the number in the denominator. Like you might be multiplying by 1/3 each time, or 1/2. Yeah, something like that. You're not going to usually have a problem where you multiply by like 13/17 each time. Or something.
Right.
Yeah, that'd be a little harder to do. Yeah. So any question on that formula? All right, so that was really it from the first part of, well, the end of the first part, and now we'll finish up the second part. Is there any questions on that? Okay. So an infinite series is one that goes on forever. Now, what do you think would happen if you added up an infinite amount of numbers? Do you think you could get an answer?
No.
No?
Maybe.
It depends what numbers you're at.
Yeah, it depends what numbers you're adding up. So if you take a number like 2, what's half of it?
1.
1. And what's half of that? 1/2. And half again?
1/4.
And again, yep.
16.
All right, what's happening?
It's getting smaller and smaller.
It's getting smaller and smaller. And eventually it's going to be pretty close to what?
0.
Right. So in this case, if you were to add up every single number from 2, cutting it in half each time, is to infinity, you actually could add these up. The only reason you can add them up is because what you're adding each time gets smaller and smaller. And eventually it becomes so small, it's like it doesn't matter anymore. Now, if you look at something like, let's double that. Okay. If you double 3, what do you get?
6.
And if you double it again, and again,
24.
and one more time.
48.
What's happening to the numbers there?
They increasing towards positive.
They're increasing towards infinity. So if you tried to add every number from 3, doubling it forever, it wouldn't add up to anything. Because it just keeps, what you're adding just keeps getting bigger and bigger and bigger. So the only way you can add an infinite amount of numbers and how to add up to something is if what you're adding gets smaller and smaller at each step. And eventually it's so small, it just doesn't make a difference. Okay, that's the main idea. Any question on that? Okay. So let's take a look. So this is what I just explained to you. There are some series that if you add up an infinite amount of terms, you actually get an answer. And there are some that you don't. The thing we want to be able to do is look at a sequence quickly and say, okay, that's going to add up to something, or no, it's not going to. So we want to be able to figure out whether it does or doesn't. So if you think practically, yeah, just I know. Could you add up an infinite amount of numbers by hand?
No.
Even if what you're adding each time is getting smaller and smaller. No, why not? Yeah.
You're wasting your time.
Why?
Because it's gonna take too long.
It's going to take too long, right? It's going to take a long time to add up an infinite amount of numbers by hand. So this is the notation that represents adding up an infinite amount of numbers. Okay. What do you notice in this notation that's really different from yesterday?
It has the infinity symbol.
It has the infinity symbol at the top. It doesn't have an n. Okay, since it has an infinity, it means it keeps going. And in the expanded notation, what do you notice is at the end? Yeah.
Another plus dot dot dot.
Yeah, it ends with a dot, dot, dot. Okay? When you expand something, if it ends with dot, 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 it means it keeps going. So again, practically speaking, we can't add up an infinite amount of terms directly. It's going to take a long time to add up infinitely many things. So we're going to look at doing it a different way. All right, I'm going to hold off on that. Let's see if we can figure out this. So this says the sum from 1 to infinity, and here is our formula. So how many terms do they want us to add up here?
An infinite amount.
An infinite amount. Okay, well, we can't really add up an infinite amount, but what we can do is we can add up maybe the first 3, or the first 4, or the first 5, and see if we start to notice a pattern. So what we're going to do now is we're going to take this, and we're going to use the formula from the last section. We're not going to add up infinitely many. Let's try just adding up 4 of them, and see what happens. So what was that formula we had from the last section? The very, very last formula.
N times N plus 1 over 2.
So a sub 1, yeah.
Oh, 1 minus R to the N.
R to the N, yep.
1 minus R.
1 minus R. Okay, so let's try that on this one and see what happens. All right, what might be helpful to figure out the first term is plug in 1 for k and see what you get. Okay, and that's the first term. So let's plug in 1. What's 1 minus 1?
0.
0. What's 1/3 to the 0 power? Yep, anything to the 0 power is 1. And then times 2? 2. Okay, that's your first term. Okay, let's get the second term so then you can see what we're multiplying by each time. What would you plug in for k to get the second term?
2.
Yep, plug in 2. What's 2 minus 1?
1.
So 1. What's 1/3 to the first power?
1/3.
1/3 times 2.
2/3.
2/3. Okay. So now let's see, what was the first term?
2.
First term is 2. So we're going to start with the 2 in front. And what do you multiply by to get from 2 to 2/3?
1/3.
1/3. Yep, R is 1/3. So I already filled it all in for you. R is 1/3. And the first term is a 2. And why is this a 4?
Because we're going to the fourth term.
Yeah, because I'm adding up the first 4 terms. Now, I'm not even going to figure out what the third term and the fourth term are. I could if I wanted to plug in 3 and 4, but I don't need to use this formula. All I need is the first term and what I multiply by each time. Okay, and that comes out to about 2.96. 2.96. Let's add up the first 5. So now we're going to add one more. There's only one thing in the formula that would change. Anyone know what the one thing is? Yeah, Kim?
It's going to change from the 4 to the 5.
Yeah, changes from a 4 to a 5. So if you add up the first 5 terms, you get 2.9877. Okay, if you type that in on your calculator. I think just by doing those two, does anyone notice what it looks like the number is getting close to?
3.
Yeah, it looks like it's getting close to 3. If you add up the first 6, you get 2.9959. So it's definitely getting pretty close to 3. The number that it's getting close to, that's the number that you would get if you added up infinitely many terms. So in this case, it's getting close to 3. Yep. So if we want to evaluate that, we'll write it up. Adding up infinitely many terms will give us 3. And that's our answer. So as you can see, we don't add up infinitely many terms. We just add up maybe the first 5, the first 6, and we look for a pattern. Right? And if it's getting pretty close to something, that's the answer that adding up infinitely many would give us. 3. Any question on that? Now, does anybody know why the numbers were getting smaller each time?
Multiplied by 1/3.
Exactly. This, what I just circled, that's the whole key that tells you whether you can add up infinitely many numbers and they add up to something or they don't. This fraction right here. What do you think that fraction has to be less than?
1.
Yeah, exactly. If it's less than 1, you will be able to get an answer. If it's more than 1, what's going to happen to each term as you keep going?
Get bigger.
They just get bigger and bigger and bigger, And if you keep adding things that get bigger, it just gets bigger. Okay? It doesn't approach anything. All right. So I'm not going to do that. Okay, let's try this one. So same directions, find the sum. But before we start it, does anybody notice anything at all? Before we even try it?
You're multiplying by 3,
Yeah.
so it's greater than 1.
Right. So, Raina, if we're going to multiply by 3 each time, what's going to happen to our numbers as we keep going in the pattern?
It's going to go higher.
Yeah, they're just going to go, they're going to get bigger and bigger each time. So, let's write out the first few terms and just see what happens. Okay. Christian, what would I plug in for k to get the first term? Yep. And then 1 minus 1 gives me 0. 3 to the 0. 1 times 4. 4. So there's your first term. And then actually, let's put a plus sign. Chris, what am I going to plug in to get the second term? Yep, plug in 2. Okay, what's 2 minus 1? Gives me 1. And what's 3 to the first power? 3, and then 3 times 4. 12, perfect. So we get 12. Now let's just do one more. Isaiah, what am I going to plug in to get the third term?
3.
3. Okay. What's 3 minus 1?
2.
Yep. 3 squared.
9.
And 9 times 4.
36.
36. So we can keep going. The problem is the numbers are getting bigger and bigger each time. So if we try to add these up, are they going to add up to anything?
No.
No. All right. So let me write this down. What happens? So when the terms you are adding are getting larger. There is no sum. And the word that we use to describe that is divergent. Okay, so we say that the series is divergent. Right. Have a great day. That's the word. Okay, so when you're adding up numbers and they just get bigger and bigger and bigger each time, and they don't add up to anything, then you say that the series is divergent. Now, when they do add up to something, does anybody know what the opposite of diverge is? Converge. Yeah. So when the terms actually add up to something, like we did in this problem, this is a convergent series. Because it's convergent, we can actually get an answer. In this case, it was 3. It's not always 3, but in this case, it was. So I'll write that down too. So when the terms you're adding get larger, there is no sum. It is divergent. If it is not divergent, then it is convergent. Now, one thing I want to just explain, because sometimes this question trips people up on the test. And I'm going to go back to the first one we did. All right, so we have the individual terms. We had 2 over 1, we had 2/3, the next one would be 2/9, 2/27, and so on. So what are the individual terms getting closer to?
Positive infinity. Oh, sorry.
3.
Zero.
2/27, that's not 3.
It's getting close to zero.
The terms are getting closer to 0 because the denominator is tripling each time. So the individual terms are getting closer to 0. What is the sum of the terms getting closer to?
3.
That's 3, yes. So in a convergent sequence, the terms are always getting closer to 0. That's the only way they can add up to something. They have to be getting smaller. So the terms are closer to 0, but the sum of the terms is 3. Is there any question on the difference between the two? Okay, that's important. So here I would say that the terms are approaching infinity, and the sum of the terms is approaching infinity. That's divergent. Okay. Question on the difference between divergent and convergent. Okay. Divergent, I already explained that to you. All right, so we've seen some problems that diverge, and we've seen some that converge. What we want to do now is be able to look at it quickly and just say, convergent, divergent. So what they do in the book is they give you the formula that we had in the last section. And they say, just try typing that formula in for different values of r. So let me put that in. So it's the same formula I gave you right at the end of the last one. And they want me to first let r be 0.8. Okay, so to type that in, you have to do it like this. 1 minus 0.8 to the x divided by 1 minus 0.8. Okay, what I'm going to do is I'm going to look at the table. And let's see what happens. When we start out plugging in 1 for x, that's the answer. When you plug in 2, you get 1.8. Now, I can't 100% tell what's happening. So I'm going to put it on table setup, and I'm going to put it on ask so I can type in what I want to see. Okay. What's a number that's further down than 10 in the sequence?
5.
How far?
5.
5 would be before 10.
Oh, so now?
Yep, so 15. All right, 4.8. Even further.
30.
30. 4.99.
60.
60.
120.
It's not really 5. If you highlight it, you can see it's 4.99999. Does it look like you're getting close to something?
I'm guessing 5.
Yep. You're getting closer and closer to 5 in this case. Yep. So would you say that when you plug in 0.8, does it converge to a number or diverge?
Converge.
That converges. Let's try 0.9. Let's change it to 0.9. Oops. 0.9. And change R to 0.9. All right, so let's look now. 15, we're at 7.9. 30, we jumped up to 9.5. 60, we jumped up to 9.9. Let's go even further.
120.
120. So this would be the 120th term down in the sequence. 9.99999. Does it look like we're converging this time?
Yeah.
Yeah. What does it look like we're converging to?
10.
10. So this one converges. So they both converge. The difference is 0.9 converges slower than 0.8. Because think about if you multiply a number by 0.9 over and over, or you multiply a number by 0.8 over and over, which one gets smaller quicker? Would be 0.8. 80% of a number is smaller than 90%. So the smaller you make this, the faster it converges. Right. Now let's try 1.1. Alright, so I'm going to plug in 1.1 and 1.1. Go to my table. Okay, so when we're at 15, the first 15 numbers in this pattern add up to about 31. The first 30 add up to 164. The first 120 terms add up to almost 1 million. So does it look like I'm getting close to anything?
Infinity.
So we are getting closer to infinity. Are we getting closer to an actual number? No. So this diverges. What do you think the difference is between this one diverging and that one converging?
One's above the number one, one's below the number one.
Yeah. So what do you think would happen with this one?
Diverge.
Yeah, it would also diverge a little bit faster, or a little bit slower than the last one.
Oh, faster. 120% faster than 110%.
Yeah, a little bit faster because you're multiplying by something that's going to make it a little bit bigger each time, a little faster. So just by trying different values, you can kind of get an idea of what converges and what diverges. Yeah.
What would one be?
One would be neither. One wouldn't be considered a geometric sequence because
Same number?
yeah, a geometric sequence has to either grow or shrink. If you multiply by 1 each time, it just stays constant. Yeah. So I won't give you one where r is 1. It'll either be more than 1 or less than 1.
Anything over 1 diverges, anything less than 1 converges, right? Correct.
Yep.
You just
So that's it right there. And even if r was negative, like if r was -4, that diverges. Okay? Any number, you want to think of it like on a number line. Here's 0, here's 1, here's -1. The stuff that converges is in this zone right here. That's the zone that converges. Any r value that's between -1 and 1. Once you get outside that zone, okay, like out here and out there, that's the divergent zone. So anything in the green, that's where you're going to converge. Anything beyond it, you're going to diverge. Any question on that? Yeah.
If one stays the same, -1, would that swap it back and forth between being negative and not?
Yeah, if r was a -1, it would alternate positive, negative.
So would that be considered a series?
If r was -1, it would alternate. No, it would still, if you added up everything, it would add up to infinity. I think it would add up. Well, actually, let me see. So if you put in exactly 1, the problem you're going to get is in the formula, you're going to be trying to divide by 0. Does that make sense? So now you're dividing by 0. So that's why you can't put in 1. That's why I'm having trouble thinking about your question. Because if I hit graph, or actually if I go to my table, it just says everything is an error. Now if you put in -1, 1 minus, let's just change that to a -1, and change, well, if you had 1 minus -1, what would the bottom really become?
Plus
1 plus 1. So if you do that, yeah, now you're just getting 0 all the time. Except, well, actually, you're getting 0 when it's an even number, and I think you're going to get 1 when it's an odd number. Yeah. So, again, not really something we would look at. I will always give you one that's more than 1. but not 1. Or less than -1, but not -1 itself. Yeah. Yeah. And the formula that it converges to, we actually don't have to go through and do this. Like try adding the first 4, then the first 5, then the first 6, and look for a pattern. It's actually an easier way. The formula that we use when we add up infinitely many things is actually easier than the formula when you're adding up a finite amount of things. That's it. It kind of looks like the formula we used before a little bit. It's got the 1 minus r in the bottom. And it's got the first term in it. But it doesn't have like to the power of n. Let's try that formula on the first problem we did. So it's a sub 1 over 1 minus r. Let's go back to it. Okay. What was the first term in this problem? 2. So let's write down 2. Let's actually use a pen. So 2 divided by, and what did we multiply by each time? 1/3. 1 minus r. What's 1 minus a third?
2/3.
2/3. And to take 2 and divide by 2/3, you take 2 and you multiply by what?
3/2.
3/2. What's 2 times 3?
6.
6. And 6 divided by 2?
3.
3. And what did we say that the sequence added up to? 3. So it's a very quick formula to see what it adds up to.
Just a quick question. If so, like on the sigma, where it says k equals 1, how come you didn't use 1 to start? If then you're saying k equals 1. That's probably a stupid question.
Well, we did use 1. We took the 1 and we plugged it in right there.
Yeah.
And that's how we got 2
Okay, yeah. Alright, you got
for the first term. No, that's all right. Any question on that formula? So this formula only applies to a convergent. You can try it on divergent. You'll get an answer, but the answer has no meaning. Okay, so you only want to use this formula on something that converges. Yeah, question?
So, to use that formula, you only need to know the first 2 terms or something?
To use that formula, you only need to know the first term, and you have to know what you multiply by each time.
So basically the first 2.
Yeah. Or somebody just says the first term is 3, and you multiply by 2/3 each time. Yep. All right, let's try it on this one. Now, first of all, you can only apply this formula on something that converges. So that's my first question. Does this converge?
Yes.
Yeah. How do you know it converges?
There's a 1/2. That's less than 1.
Right. If the r value is somewhere between -1 and 1, it will converge. 0.5 falls in that range. Okay, it's the green that I highlighted on the number line. Okay, so what's my formula to figure out what an infinite sum converges to? Don't have to fill it in, just tell me what it is.
A1 divided by 1 minus r.
Yep. A1 divided by 1 minus r. Okay, so let's figure out the first term. I think you'll start to figure out what the first term is without doing this in a minute, but what do you plug in to find the first term? 1. What's 1 minus 1?
0.
What's 1/2 to the 0? 1. And what's 1 times 5? 5. This is always your first term. Whatever number is right there. Okay, so the first term is 5. And what are you multiplying by each time? What's the r value? Yeah, 1/2. So this, that's your R. And that is always your first term. Okay, that's the formula for a geometric series. We talked about that on Monday. A1 R to the n minus 1. In this case, it's just k. Okay, so now let's see, what does that come out to? What's 1 minus 1/2? Yep, that's going to be 1/2. And what's 5 divided by 1/2? What is it? 5 divided
5 times? No.
Not 5 divided by 2. That would be 5/2. This is 5 divided by like 0.5. Think of it that way. 10. That's 10. So, what is the 10? What does that mean?
That's what it's getting closer to.
Exactly. This is what it's adding up to.
That's what it's converging to.
That's what it's converging to.
That's what you'd say.
Yep. So this sum is converging to the number 10. Does it ever reach the number 10? No, but it gets infinitely close to it. So the first number is a 5. And then the next number is half of it. So 2.5. The next number is 1 1/4. And you can keep going. And if you add up every number from 5 to infinity, cutting it in half each time, it will add up to 10. Or get extremely close to 10. And that's how you find the sum of a infinite geometric series. Any questions on that? All right, so what we can do, with the time we have left, I can put a list of topics. Okay, that'll be on the test. And we'll have plenty of time if you want to ask me any questions. So that's the homework. And let me put a list of test topics. Okay, so I took off 2 of the questions after number 22. And then for 38 and 39, don't do what they're asking. They ask you to use a graphing calculator. We didn't really do it that way. Just use the formula a sub 1 over 1 minus r.